So we did the water conservation equation for unsaturated porous media, where we considered capillarity and also gas pressure. Almost a complementary situation is when the matrix, instead of being unsaturated, it stays saturated during the process. And if it stays saturated, then the capillary pressure is zero, and also gas pressure is zero, because if it is saturated, there is simply no room for gas. So gas pressure is zero, capillary pressure is zero. And so if we can ignore the gravity, we can write water pressure is equal to the swelling pressure. So when can this happen? This actually can happen during meat cooking, where as you heat, the meat shrinks. So even though it is losing water, it can still stay saturated. And so meat cooking has been modeled using this assumption of the P water, the pressure of water is equal to the swelling pressure. So swelling pressure is the only driving force in this case, and it is almost a bit complementary to the previous one, where capillary pressure in unsaturated porous media was the primary driving force. Here, the porous media stays saturated. So for swelling pressure driven transport, I can write the flux of water due to swelling pressure this way. Where NW is the flux and del PS del X is the gradient in swelling pressure. Now, I already mentioned that this worked out well for modeling meat cooking. So meat cooking is an example of this swelling pressure driven transport. So for this kind of transport, in case of meat, swelling pressure PS is given by some constant multiplied by the difference between concentration of water at one point and the equilibrium concentration at that point as a function of temperature at that point. Okay, so in other words, at higher temperature, the equilibrium concentration in meat is going to be lower, so it's because the meat can hold less water. So since PS is a function of CW, how much water is there, and the equilibrium concentration, which in turn is a function of temperature, so PS is a function of CW and T, so we can write it as PS, the derivative of PS, as del PS del CW times del CW del X, and also del PS del T times del T del X. Write it as the chain rule because PS is a function of CW and T. Okay, so then this part of it can be interpreted as diffusivity due to swelling pressures dependent on water content, and then this part of it can be interpreted as diffusivity due to swelling pressures dependence on temperature. So if I now plug in for PS, so I plug in for PS in here, then I get minus rho W K over mu E times del CW del X. So I'm taking the derivative of PS. E times del CW del X. Likewise, for the second term, it will be K over mu times del PS del T. So if I take a derivative of this with respect to temperature, and its partial derivative, so which means CW would be treated as a constant now. So I write K over mu, because PS has the K over mu, times del PS del T, which is same as this del CW equilibrium del T. So it's this guy. Whereas the first one would be this. Okay. So now all of these together can be thought of as some sort of a diffusivity. So this one is diffusivity of water due to the swelling pressures dependence on water content, and then this one is due to swelling pressures dependent on temperature. So this gives me water flux due to swelling pressure, which we would now put into the conservation equation. So now, substituting this flux equation that we just derived into the conservation equation, this is the water conservation equation. If I substitute that, then I can simplify further and develop the conservation equation or the transport equation for water when swelling pressure is the driving force. Those details of the derivation, I leave it up to you to simply plug this in and develop the algebraic expressions. I'm not going to do them here. So this map or flowchart is going to try to summarize the water transport. Now, since this kind of a map or chart have not been introduced before, let me spend a little bit of time explaining the chart. So transport in this case of water can be as bulk flow or as diffusion. The phase that we're talking about is water, and then the bulk flow of water happens due to gas pressure as the driving force. So driving force for flow of water is the gas pressure, but driving force for diffusion of water it can be capillarity. If the matrix is unsaturated, it can be capillarity, or it can be swelling pressure when the matrix is saturated. So those are the possible driving forces for diffusion-like movement of water, and then gas pressure is the driving force for flow. Plus we have the source term, evaporation, where water becomes vapor. So for water, the term is negative. So this shows the modes of transport and the driving forces for water. So we're going to use this kind of a map for other transport, and that will fill these empty spots that we don't see at this moment.